Bond energy and Lewis structures. We're going to be talking about bond energies. This is kind of a new topic for us. To break bonds, energy must be added to the system. So if we have a molecule and I want to break it apart because I want to rearrange it in some sort of chemical reaction, energy has to be added to the system, and therefore the molecule has to absorb that energy. Thus it's endothermic. To form bonds, however, after the bonds have been broken in the reactant phase to becoming the products, energy is then released, which is exothermic, and therefore a negative delta H, a lower energy state. How to calculate bond energy, or delta H? It is the sum of the bonds broken minus the sum of the bonds formed. So let's look at the delta H for this following reaction. Here we have one molecule becoming another one, some sort of rearrangement. It almost looks like carbon has switched places with nitrogen. And we're given the following information. In other words, the energy stored in the carbon-hydrogen bond right here is 413 kilojoules per mole. For carbon and nitrogen, it's 305. Carbon-carbon bond is 347. And carbon triple bond nitrogen is 891. Notice that the number of bonds, as the number of bonds increase, so does the bond energy, because it takes a whole lot more energy to break a triple bond than, for example, a single bond. So, how can we predict the delta H for the following reaction? Let's see how to do it. Well, the first thing you have to do is you have to think of how the molecule is put together. CH3N triple bond C. In a little while I'm going to show you some Lewis diagrams, and it's actually easier that way after you know how to do that. But this section came first. So what you have to do is you have to put this molecule together. Carbon bonded to 3 hydrogens, bonded to nitrogen, triple bond, carbon, becomes carbon bonded to 3 hydrogens, bonded to carbon, triple bond, nitrogen. Essentially that's what's happening in this particular reaction. And remember, it's bonds broken minus bonds formed. So we have to figure out how much energy it takes to break the bond of this first molecule right here. Well, you will notice that there are 3 carbon-hydrogen bonds, 1 carbon-nitrogen bond, and 1 nitrogen-carbon triple bond. So what I have to do is I have to figure out whatever 3 times 413 is, because for each carbon-hydrogen bond it's going to take 413 kilojoules of energy absorbed to break it. So 3 of those plus a carbon-nitrogen bond, which is 305, plus the carbon-nitrogen triple bond, which is 891. That's how much the bonds broken is, minus the bonds formed. Now, on the other side we have 3 times 413, plus a carbon-carbon, which is 347, plus an 891. That's the carbon triple bond nitrogen. So it's pretty easy to figure out, and when you do the math, I think you get negative 42. Yep, delta H is negative 42 kilojoules, which means the overall reaction, of course, is exothermic. Now, the picture that I drew before, of course, is a Lewis structure. What is a Lewis structure? A Lewis structure shows how valence electrons are arranged among atoms in a molecule. And it reflects the central idea that the stability of a compound relates to the noble gas electron configuration. Remember, within a bond there needs to be 2 electrons, or a dash. We use the dash diagram. Hydrogen forms stable molecules where it shares 2 electrons, and you can see that's the dot diagram. Alone, hydrogen has 1 valence electron each. Together, it shares the 2 electrons, and that's what it looks like. The octet rule, of course, says that elements form stable molecules when surrounded by 8 electrons. So you have to have 8 electrons. So knowing those two things, we're going to talk about bonding. And of course there's single bonds and double bonds and triple bonds. A single covalent bond is a bond in which two atoms share one pair of electrons, like in this molecule, H2. The double bond is where two atoms share two pairs, like this one. And of course a triple bond, where two atoms share three pairs of electrons, like in N2. So how do we write Lewis structures? Well, we have to add the valence electrons from all the atoms in the molecule. Use a pair of electrons to form a bond between each pair of bound atoms, and the atoms usually have noble gas configurations. Arrange the remaining electrons to satisfy the octet rule or duet rule for hydrogen. So we're going to sum the valence electrons from all the atoms in the periodic table. So here's the example H2O. And I'm going to do it first, and then I'm going to see what they say. So this is how I would do it. I would go to the periodic table, and I would notice H2O has two hydrogens. So each hydrogen has two electrons, one electron, and there are two of them, so a total of two, I should say. Oxygen has 6 valence electrons. There's only one of them, so that means 8 electrons total. So this diagram, this Lewis diagram, is going to have 8 total electrons, but it's easier to do the dash diagrams. So what you do is divide by 2, and you get 4 dashes. The rule is every atom except hydrogen needs 4 dashes. So all atoms need 4 dashes. Hydrogen needs 1 dash. And this is true for covalent compounds. Ionic doesn't work so well for. Oops, there we go, 8 total. Oh, and let's see, do they tell me? Let's see if they use, all right. So this is how they do it. They do HOH. Now, use a pair of electrons to form a bond between each pair of bound atoms. So we need 4 dashes. We know we have to kind of stick the 2 hydrogens around oxygen. And then finally, we have to make sure that we all have 4 dashes. So there's H2O. And you'll notice they're showing the lone pairs as actually literally lone pairs. I tended to write things that looked like this. Of course, it's also at a bit of an angle, but you get the idea. It doesn't really matter to me if the lone pair is actually a line or a pair that's alone, like what you see here. So let's figure out the answer to the next group. I haven't looked ahead to see if they show you these structures, so I'm going to assume they might. But let's go through them anyway before we see the answers, because I don't want to cheat. PBr3. So I go to the periodic table and I look up phosphorus. Now phosphorus, I'm going to move it around a little bit. Sorry for any noise I'm creating. Phosphorus has 5 valence electrons, and bromine has 7 times 3, which is 21. So that's 26 dots, or 13 dashes. So I have to have 13 dashes for PBr3. The atom that is the one of a kind is 99.9% of the time in the middle. So P, and then you have 3 Brs. You can put them anywhere. I'm going to put them here. I have 3, and I need 13. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and now number 13 has to be a lone pair above bromine, above phosphorus. So that's how I would do that one. And of course what we did, and we will eventually do in our next unit video, will be to talk about the VSEPR theory, valence shell electron pair repulsion theory, which will help us figure out the shape of that particular molecule. Alright, so that's what PBr3 would look like. And then finally HCN, how to do that one. Hydrogen has 1 valence, carbon has 4, and nitrogen has 5. So 5 and 4, 9, and 10 dots, or 5 dashes. And again, everything has to have the correct number. So carbon is always in the middle, so I know that. And I have 2, and I could put some, maybe some lone pairs over carbon, but I'm going to tell you, carbon never has a lone pair. So even though that might sound like a good idea, I can't do it. Nitrogen might be able to, but if I did, you see that? That's 3, 4, 5. And that's fine, that has 5 dashes, but carbon is not satisfied. So we have to have a multiple bond, like a triple bond. And so 1, 2, 3, 4, 5 is the correct answer. Oh, there they go. Look at that. They show you the answer. Huh. And in these diagrams, you can see that they use the lone pair as literally dots of 2, which is fine. You can do that. And they use the bonding pair as a line or dash. All right, so let's draw a Lewis structure for each of the following molecules. Some of these are pretty easy. H2. Well, each hydrogen has 1, and so H2 will just look like this. Dash H. I'm not sure why I made that hydrogen look different than the first one, but there you go. All right, next one is F2. Fluorine has 7 valence electrons. Times 2 is 14. Divided by 2, we're back to 7. So we need 1, 2, 3, 4, 5, 6, 7. Now, according to your book and probably this PowerPoint, maybe they would rather see this. And then you could actually see the lone pairs, which is helpful, but sometimes, especially in really large molecules, these lone pairs, if we have too many dots of them, can look confusing. So that's actually why I prefer the one I drew in the beginning. And then HF. Right, hydrogen has 1, fluorine has 7. That makes 8 dots, or 4 dashes. So we need 4, 1, 2, 3, 4. Remember, hydrogen only needs 1 dash. So once I put hydrogen down and bonded it to something, I don't need to worry anymore, because I have to, I can't put any more around hydrogen. So those are the Lewis structures for each of these following molecules. All right. Let's try these. Draw a Lewis structure for each of these following. These are a little bit more complex. Not too bad, though. No exceptions. Towards the end of this series of videos, the very last video I'm going to be talking about will be exceptions and resonance structures. So this is a little bit different. And I think it actually comes earlier in the book, but I'm waiting to save it until we talk about Vesper theory first. All right. So first one is ammonia, and H3. Nitrogen has 5, and the 3 hydrogens have 3. That's 8 or 4 dashes. Nitrogen's in the middle, and the 3 hydrogens. 1, 2, 3, 4. You'll notice that each hydrogen's already satisfied, and the extra lone pair, if there are extra lone pairs, even when we have expanded octets, will go on the central atom. All right, the next one, CO2. Carbon has 4, oxygen has 6 times 2, which is 12, so that's 16 dots or 8 dashes. So what do we do here? Well, carbon's always in the middle, so the 2 O's have to go on the outside, so we need 1, 2. Carbon never has a lone pair, so 1, 2, 3, 4, 5, 6, 7, 8. You might say, well, that looks mighty fine, has 8 dashes, but you'll notice carbon is not happy. But that's why we have multiple bonds. Because if we take one of the what used to be lone pairs of carbon dioxide, put them in as double bonds, then we have a situation where carbon has 4 and oxygen has 4, and therefore that is carbon dioxide. And then finally, CCl4, carbon has 4, chlorine has 7 times 4, which is 28. So that's 32 dots or 16 dashes. Carbon's in the middle. We know we're going to have 4 chlorines, and that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And remember, we needed 16 dashes anyway. There we have it. And that's the shape of CCl4.